My name is Leming Wang. I'm co-hosting the transportation seminar with Professor Chris Monsieur this term. Today we're very pleased to have one of our own, Alex Bigazzi, to talk about a topic I think a lot of us here in the room have personal interest about measuring the cyclist uptake of transportation-related air pollution. With that, I will just forgot to introduce Alex. Alex is a third-year PhD student in the civil engineering program here at Florida State. With that, I will just give the floor to you.
Great. Thank you very much, and thank you all for being here. Before I dig into this thing, I'd like to acknowledge my co-authors or co-researchers on this topic. Miguel Figliozzi is my advisor and my dissertation committee chair. Jim Pankow is also on my dissertation committee, and he's also the PI on a project in which we're doing some empirical measurements, which I'll be talking about a little bit later. And then Wentai and Lauren are research associates that work with Jim in his lab over in the engineering building. So thanks to them. So we're going to be talking about measuring bicyclist uptake of traffic-related air pollution today, and it's going to be a little bit of a mix of early results from some ongoing empirical research that we're doing, as well as conclusions from exhaustive literature review that we did last year, and that's going to be published next month in Transport Reviews is the journal. So first, the very broad context for what we're talking about here. So as most of you know, that bicycling is enjoying somewhat of some encouragement in cities around the world because of a host of expected benefits. And one of the big expected public health impacts is an increase in physical activity or increase in exercise. And that has been pretty well established, but there are also other impacts of bicycling on public health. And that includes possible changes in crashes, crash frequency, crash severity, and possible changes in air pollution. And air pollution is what we're focusing on. And there are two big effects of air pollution changes if there's a shift towards bicycling. And one of them is a reduced total amount of emissions as people assumedly drive less. And so that would be a good thing. But there's also the potential for increases in exposure and doses, pollution doses for the cyclists. And that would be a bad thing. And that's where we're focusing today. And I think it's a particularly interesting topic because it directly ties into one of the main public health benefits of an increase in bicycling, because increases in exercise directly drive increases in air pollution doses. So it makes it a pretty interesting interconnected topic. And then the other thing I'd like to do before we get into the main content is get everyone on the same page. And this is the 6 steps in traveler exposure pathway from vehicle emissions to the health effects of those emissions in terms of pollution exposure. So first we have vehicles emitting generating and emitting a number of pollutants, and combine that with the meteorology and atmospheric processes, we get air quality in a region, which is the upper right box there. The third box, if we combine the air quality in the region with what we know about how and when travelers move in the city, we get their exposure concentrations. Then, in order to get the next step, we have to consider their respiration characteristics, right? So that brings us to inhalation, the 4th step. So that's exposure concentrations combined with respiration. We get inhalation doses. The 5th step would be uptake doses. So that's not just what we inhale, but what we actually retain in the body, what we uptake and absorb. And then finally, the uptake doses are the direct cause of the health effects, health outcomes. So uptake itself is not such a problem unless there are negative health effects of that uptake. So the last 4 steps are what we're going to be talking about today. And we'll go through 4 sections. First, exposure, then inhalation, then uptake, and finally a little bit on health effects. So that's the outline. And as I said at the beginning, as I go through this, I'm going to be talking a little bit about the literature and then give you a taste of some early results from empirical work that we're doing here. So first, bicyclist exposure to air pollution. So an exhaustive survey of the literature found 42 studies ever that have measured and published on-road bicyclist exposure concentrations. This is just their exposure concentrations. And here you see just a count of the number of studies that have measured a number of pollutants here. And a couple of these abbreviations, CO is carbon monoxide. VOC, which we'll see a couple times today, is volatile organic compounds, and these are carcinogenic gases. There is NO2. The bottom four are all particulate matter. PM means particulate matter, and so these are, instead of gases, these are fine particles. And they come in three kind of size range. Ultrafine are the smallest, coarse PM is the largest, and then black carbon is directly soot related, so it's dense carbon structures in there. So there have been a number of measurements, like I said, 42 in the history. And as we look at them, the central values of these studies vary extremely widely. And I just threw up a couple examples here. So for carbon monoxide, 1/2 to 13 is the central value reported from these studies. So these aren't the ranges reported, but the average or median exposure concentrations for bicyclists has been reported over a wide range. For ultrafine particulates, anywhere from 9,000 to 94,000. So order of magnitude differences here. So it's really not easy to say this is a representative exposure concentration value for bicyclists. It really depends on the context, which isn't too surprising, but it's a little problematic because this is really a European-centered area of research. Most of it's been done over there. So a little bit happening in Australia, New Zealand, in China, but there's only been 3 in the United States since the 1970s. And we have essentially different vehicle fleet and city structures from Europe. So we'd expect exposure concentrations to be different from those in Europe. So really lack of empirical data about exposure concentrations in United States cities. So a common approach to assessing or to studying bicyclist exposure is to compare it with other modes. And that's a very popular research question. More than half of those studies, that was what they were looking at. So bicyclists versus bus riders versus automobile passengers, et cetera. And it turns out that the results are pretty inconsistent. So we can't say across the board we expect cyclist exposures to be higher or lower than other modes. The exception to that is if the bicyclists in the study are using a separated bicycle path along a river or through a park area, for example, then they are pretty consistently lower. But other than that, it really just depends on how they conducted their study design. So what kind of facilities they had the bicyclists riding on, what kind of facilities the drivers were driving on, and where the buses went. So there's a fair bit of inconsistency across studies. And one other problem with this type of research is that they tend to fix an origin and a destination and just look at travel by modes between point A and point B. And we know that bicyclist travel patterns tend to be different from motorized travel patterns, right? They tend to be shorter duration or shorter distance trips and in higher density parts of the city than motorized travelers. And that's typically excluded from consideration in these studies. One more limitation of this type of research is that what does it tell us as transportation professionals? So what kind of information does this give us about designing and planning our transportation systems beyond whether or not a mode shift towards bicycling is good from a pollution point of view? Well, it doesn't tell us a whole lot, right? So if we just compare bicycles to buses, it doesn't tell us much about how to reduce exposure for bicyclists or for bus passengers either, right? We need to look in more detail at the intramodal variation here. So like I said, there has been some analysis comparing exposure in different conditions for bicyclists. And the main thing that's been studied is high exposure versus low exposure bicycle routes. So here's a summary of the studies that did do that for 6 of the pollutants here. And you can see the number of studies that consider this. And what we see here is the median and the range of the reported % differences in exposure on high versus low traffic routes for bicyclists. And some of them get pretty high. So for VOC, that was the volatile organic compounds, there's the biggest difference between high and low exposure routes. Whereas on the other end, for PM10, which is the coarse particulate matter, there's essentially no difference. And that's not too surprising because PM10 traffic contributes a much smaller portion of the PM10 pollution in an area than it does for VOC or for UFP or even for black carbon or carbon monoxide. So these follow generally expected patterns if you compare them among the pollutants. These are pretty big differences, right? So for a few of these in the 50 to 100% difference range. So like I said, so that's kind of what we know from the literature. And like I said, we've been doing some research on this here at Portland. And the focus of what we're doing is to get in a little more detail at variation around the city. And so not just comparing modes, but saying, OK, how can we better design a better plan, assuming that some people are going to be riding bicycles? How can we reduce their pollution exposure levels? So we have an instrumented bicycle with a whole bunch of stuff on it. And we did a sampling campaign around the city over the past spring and summer mostly, and a little bit into fall. And so there's a whole bunch of stuff on here, and I'll kind of point it out. So we have some high resolution, so second-by-second measurements of carbon monoxide, carbon dioxide, not as a pollutant of concern, but as an indicator of the presence of traffic emissions. Particulate matter, TVOC, that's total VOC. So it kind of aggregates all the VOCs together. And we also have a sampler pump and sampler cartridge, so we're taking whole air samples and then bringing them back to the lab. And Dr. Penkel's lab analyzes that for really detailed gas characteristics, so about 120 different compounds there. In addition, we're doing some breath sampling, which I'll talk about later. And then we have all our travel characteristics we need to measure. So we have a smartphone, which we're interacting with, cameras, front and rear, cyclocomputer looking at speeds, and we have the ACE device, which I'll explain next. If it's a clarifying question, we could do it now? Yeah, sure.
What's VOC mean again?
So VOC is volatile organic compounds, and it's a class of pollutants. And there are actually thousands and thousands of VOCs, and hundreds and hundreds which are directly associated with motor vehicle emissions. So does that answer your question? Yeah. Sorry. OK, so the Portland ACE. So the Portland ACE and the smartphone are kind of linked up here. So I just kind of wanted to tell you what we're doing with that. So the Portland ACE is a pretty awesome acronym for Portland, low cost, no, wait, portable, low cost, and network device for assessing cyclists' exposure. So like, sink that in a little bit, right? That was good. So we call this the ACE, and this served a couple purposes in this research. So what it is, it's a combination of a prototype device we built and then a custom smartphone application that we built. And these two things talk to each other over Bluetooth. And they integrate a whole bunch of sensors in addition to the smartphone sensors. So we're looking at things like GPS, temperature, humidity. It's got a rangefinder so you can see passing cars. And it has some 3D acceleration and then some low-cost air quality sensors. It also is able to integrate data from third-party physiology sensors that have Bluetooth radios in them as well. And it combines this all with a single timestamp. So that's the first main thing it's doing for us, is that we have a lot of data streams here. And if we're looking at second-by-second data, there's a lot of processing that needs to happen so that it gets correctly geocoded with the GPS, right? So that's the main function, is synchronizing all these disparate data sources. The second thing we're doing is testing these low-cost sensors and seeing whether they can be a good proxy for the very expensive other equipment that we're using in this study. So that's more of just a kind of a field testing of the prototype device. And the reason for that is the data collection bicycle is on the scale of $10,000 to $15,000 worth of instruments on there. And not only that, but thousands of dollars worth of annual calibration costs for it. So this is really quite a costly endeavor, and is limiting the spatial and temporal extent of the data we can get. So we're looking for alternative ways that we can kind of crowdsource this data by making a whole bunch of cheap sensors and deploying them throughout the city and seeing if we can get representative values at the same time. So that's an ongoing project. So here's the type of high-resolution data I'm talking about, where you see these are second-by-second data points where the height of the pin is the TVOC exposure concentration. And we see things like over here this is facing south. So over here by the river in southeast Portland, you see some high exposures, as you might expect. There's a lot of traffic and light industry here. And you can see there's also where there's a vertical cut in the roadway, so you have poor dispersion characteristics. We also see some individual scattered high spikes where you might not expect it in, say, low-volume local streets. And so that's why the video data are important for going back, seeing these things, and we can look at the video. And in this particular example, that blue car didn't see the stop sign and pulled his foot off and stalled the car in the middle of the intersection, and then restarted it right before our probe cyclist went through the intersection. Right, so that explains a really high spike. So that's not necessarily a characteristic of the street, right? It's a characteristic of an isolated event. So that's why it's important to get a lot of different data. So here's the extent of the sampling campaign. We have about 40 hours of usable second-by-second data spread out over 13 days. And you can see we tried to cover a whole lot of different facilities. I'm not going to be presenting all this data today because it's still an ongoing process to analyze it all. But to give you a feel for the variability that we're looking for, all the way from very high volume streets like Powell, thank you, flaking out, Powell, in addition to some of the off-street paths. But here is a taste. So this is some of the early results, and we're looking at BTEX compounds, and that's an abbreviation: benzene, toluene, ethylbenzene, and xylene. And these are 4 of the major VOCs that are related to traffic. Right? So these are vehicle source VOCs. And we categorize, so this is the modeled concentration increase expected compared to Tabor. And so Mount Tabor Park, we did some early screening analysis. We found that that's a nice low urban clean background reference exposure concentration. So we took that as our reference, and we measured it at least once during each sampling period. And these are about what you'd expect, right? So the arterials have quite a lot higher exposure than at our clean reference location. Local roads also higher than the clean reference location, but not nearly as much as the arterials. I-205 is around the same exposure concentration as the local roads. Might be a little surprising because I-205s carry such high vehicle volumes, but the cyclists are pretty far separated from the roadway. They're also part of the time behind a sound wall, which has been shown in other research to significantly reduce concentrations immediately behind the sound wall. In addition, the 205 corridor has pretty good dispersion characteristics over most of it. So it's pretty open, so you can get a lot of dilution of the pollution. And then if we compare this to the high-low exposure, if we look at, say, local roads versus arterials, it's about on the scale of the high-low exposure comparisons that I showed in a previous chart from the literature for VOC. So it's looking like we'd expect, but we're going to be able to go into more detail here in terms of different functional classifications of the roadways. Okay, so that's exposure concentrations. And it turns out that's where most of the research has stopped. So, but we want to go past that, right? We're going to go 3 steps past that today. So inhalation of air pollution starts with exposure concentration, and there's a couple more things that we need to assess the intake dose. And one of those is the respiration. And it's also called ventilation rate, and that's the volume of air inhaled per unit time. And then that would get us to the intake dose per unit time, but we multiply it times our trip duration, and we get a total mass inhaled over the trip. And so you know the respiration is usually split into 2 components. We have the tidal volume and the breathing frequency. So that's the amount inhaled per breath, which is about ½ a liter to 2 liters, depending on your exertion level, and then the breathing rate, so the number of breaths per second. So respiration or ventilation has been shown to correlate very strongly with exertion level, workload, and heart rate. And in some research from, I believe it was either Belgium or the Netherlands, they had statistical fits of like 97% on an individual basis in terms of the relationship between heart rate and ventilation rate in terms of volume per minute. So really strong relationships here. So a steady increase in ventilation as we're exerting ourselves in general. So what does this mean for bicyclists? Well, there are 2 main pieces determining bicyclist exertion levels. So there's the external work they're performing, and there's also some personal characteristics. So the external work they're performing are the physics of the bicycle system. So you have speed and acceleration, the weight of the bicyclist and the bicycle, the slope, wind and drag, rolling resistance in terms of the characteristics of the tires and the roadway surface. And all these things, we use physics, and it's not too hard to calculate that. So that's the external work that's being done. And that actually is the major effect. There's also some personal influences, personal factors influencing the total energy expenditure while you're bicycling. One of those is the basal metabolic rate. So that's just the energy we're expending to perform basic life functions. That you all have a basal metabolic rate going on. I probably have a little higher basal metabolic rate going on because I talk with my hands a lot. All right, so that is added to this. But it turns, and then there's also fitness levels. So trained athletes or endurance athletes will have slightly different ventilation responses to workloads. So that's a modifying factor there. But it turns out that the external work is really the main factor. And so even a really fit person, if they're riding the same bicycle in the same way, they're going to have similar increases in ventilation while they're bicycling. So in this way, it's really the transportation system that's driving, sorry, pun, the transportation system that's driving the inhalation rates beyond the exposure. Okay, so transportation system is important for respiration. So how has this been handled in the literature? Well, if we expand it, so we started with 42 studies that directly measured bicyclist exposure concentrations. We're going to add in 15 more studies here that didn't directly measure it, but modeled it in some way or used some other proxy for exposure concentrations. So 57 studies assessed cyclist exposure in some way in the literature. Of those, 38% ignored respiration, and they only looked at exposure concentrations. These are mostly modal comparisons that just didn't want to get into it. The remaining 19 did look at respiration. 16 of those used a constant respiration rate. They said, and again, these are almost all modal comparisons. So they said automobile drivers have a respiration rate of 11 liters per minute, and bicyclists have a respiration rate of 25 liters per minute. Done. So we're going to scale the exposure concentrations accordingly. So that really only helps us if we're only interested in modal comparisons, right? But that doesn't tell us, again, much about how the transportation system affects intake doses. And almost half of those just used an assumed respiration rate based on someone else's studies. So 3 studies so far have considered variable respiration rates. And a couple of them just varied them by individual. So they said this person's bicycling respiration rate is this. And there's been 2, and the other 2 looked at variation as they traveled around. I think they aggregated it to 1 or 5 minutes. So they said, you know, minute by minute, here was this person's respiration rate. And only 2 have measured them in the field at all. So most of them are modeled where they have someone on a stationary bicycle. They develop respiration heart rate relationships, and they measure heart rate in the field and then estimate respiration based on the measured heart rate. So not a whole lot of direct measurement of on-road respiration and not a whole lot of consideration of how it varies within the transportation system. Here are some of the studies that did measure bicyclist respiration or modeled it based on heart rate. As you'd expect, it increases with bicyclist speed. This is, these are the combined results of 8 different studies that report both speed and respiration. And here we're comparing it to a typical motorized vehicle passenger. So one would be the same, and what we see is that for the most part, bicyclist respiration rates are 2 to 5 times those of motorized travelers, increasing with the average speed of the bicyclists. All right, and this all pretty well makes sense, and not enormous differences there between men and women either. So what do the modal comparisons of intake tell us? Well, like I said, there aren't too many of these because most people have ignored respiration, so they didn't go to intake. But the 2 to 5 times higher respiration rate for bicyclists than passengers, combined with often longer duration, means consistently greater intake doses for bicyclists than for other modes for similar distance trips. And this contrasts with what we saw in terms of exposure concentrations, right, where it was really contextual, it depended. Here, intake doses consistently higher for bicyclists than other modes, and respiration is a big factor driving that. So here's a comparison of 5 studies that looked at PM 2.5, 3 that looked at ultrafine particles, and 3 that looked at carbon monoxide, comparing bicyclists with other modes. So this is the difference from bicyclist dose. So down means lower. So car, taxi, and bus modes are quite a bit lower on average in terms of intake doses for similar trips than bicyclists are. Whereas pedestrians are pretty well mixed, because pedestrians also have elevated respiration rates, not as elevated as bicyclists, but they're also a lot slower, so they have longer exposure durations than bicyclists. Another interesting question that's been asked is duration versus respiration. So for active modes, bikes and peds, speed has two effects. So if you go faster, you're exerting more energy, so your respiration goes up. But you're also in the exposure zone for less time. And one study has looked at this issue, and they did some modeling and determined that it's duration that dominates. So if you go faster, the shorter time of being exposed dominates the increased respiration. But like I said, this is one study that looked at this, and they certainly didn't cover all possible scenarios in terms of, and the maximum speed they looked at was 18 miles an hour. So up to a point. So what are we doing with this stuff? Well, this is another component of what we're looking at. And so we're using a chest strap to measure second-by-second respiration characteristics for the bicyclists, so breathing rate and breathing amplitude. And we're trying to look at respiration in much more detail, again, and relating it back to transportation system characteristics. And what we found so far, there is about an 8% significant positive correlation between the second-by-second total volatile organic compound concentrations and the breathing rate. So what does this mean? Well, this is a bad correlation from inhalation dose perspective, because that means that the places where the bicyclist respiration is high is also where their exposure concentrations are highest. And this kind of makes sense. So this would happen because both bicycles and automobiles are having to exert more energy either by burning fuel or by increasing their oxygen intake. And this happens at places like hills or an intersection when you're accelerating out of the intersection. And this is something that's totally missed with constant respiration rates, as you've seen almost all the literature uses. So this is exciting, and we've just barely started to dig into this data, so we want to look at it in a lot more detail in the months to come. Okay, step 5, uptake doses. So uptake doses are, as I said, not just what you inhale, but what you keep in your body. So what sticks, essentially. So we're going to start this off with some lung fun facts, because as I've been doing this work, I've been studying respiration physiology, and it is awesome. So maybe you already know. So if there's any MDs, you're not allowed to answer. The gas exchange area of your lungs is about how many square feet? Let me hear some guesses.
100.
100 square feet. 1,000 square feet. 2 more guesses, and I'll go on. I'm not going to go on it.
101.
Ah, I didn't define the game. That's true. Okay, we'll take it there. So it's 800 square feet. It's about the size of a 2-bedroom apartment. You were pretty close. That's big. It's big, especially considering your total lung volume of the gas exchange area is around 4 liters or less. So this is a massive amount of surface area. And it's only about 0.2 microns thick. So for reference, a human hair is about 100 microns. So this is about 1/500th the thickness of one human hair spread over 800 square feet. So this is a massive area of exposure of your internal body systems to essentially environmental air, right? So it's great for gas exchange, but it's also bad in terms of health risks of exposure. All right, one more. During exercise, a red blood cell spends about how many seconds in the gas exchange area of your lungs as it's moving through?
0.1.
0.1. That's a pretty good guess. We're just going to take that. It's about a quarter second. So in a quarter of a second, the red blood cell moves through the respiratory region of your lungs, and yet in that quarter second is enough time for the O2 for the oxygen to fully diffuse into the blood and the CO2 to fully diffuse out. It happens in a very small fraction of a second. Complete gas exchange takes place, right? And that's because it's so thin that there's very little resistance to diffusion. So we have this massive gas exchange area happening, which is great for taking in the energy we need and dumping our waste CO2, but it's dangerous from a pollutant point of view. So the question of uptake is the question of what happens to the gases that we've inhaled. And here are the main 3 things that are happening. One, some of it is just immediately expired. And a lot of this is in our dead space air. This is the regions of the lungs where gas exchange doesn't happen. It's kind of like if you're drinking through a straw, there's a little bit left in the straw after you're done drinking, right? And it just goes back into the cup. So some of it just goes back out. Some of it is absorbed and desorbed onto the lung lining. So your lungs are lined with kind of a liquid mucus membrane, and some highly water-soluble compounds will absorb into that. Some of them will desorb later, and some of them will then diffuse into your tissues. But a lot of them make it all the way to the gas exchange region, into the alveoli. And there, they follow the same very rapid diffusion pathways that oxygen and CO2 follow, and they will diffuse into your blood cells, so basically dissolve into your blood. Or once you leave a high concentration environment and you get into a clean air, they will desorb from your blood, and you'll breathe some of them out. But as you've absorbed it in your blood, what happens is it's processed and metabolized quite often by body systems such as the lymphatic system, the liver, the kidney, things like that. And you'll turn them into metabolites, other compounds. It's particularly bad for benzene, and some research has shown that the most dangerous part of benzene is actually not the benzene itself, but the metabolites that your body turns the benzene into as it's trying to break it down. So what happens to inhaled particulate matter? Well, this is quite different from the gases. So inhaled particulate matter, again, some of it we're just going to breathe back out. We're not really going to interact with it in any way. The larger particulates will get trapped in the upper respiratory airways and also, or the upper respiratory tract and also your mouth and nasal region. And that'll get expelled either through coughing or sneezing or swallowing. The medium-sized particulate matter will get deposited onto your conducting airways. This is mostly PM 2.5. That'll land on your into your conducting airways, and it gets cleared by the mucociliary elevator, which is awesome. And it's basically a layer of mucus lining in your respiratory tract that continually moves up and transports deposited particles into your throat where you swallow it, and then you clear it through your GI tract. And it's moving at about 1 or 2 centimeters per minute, just constantly moving by the millions of little cilia that just wiggle and push it up. So then it's cleared out of your respiratory lining. Now, the smallest PM, the ultrafine particles especially, will make it all the way through to your alveoli, or the gas exchange area. And these, the mucociliary mechanism no longer works, because here we want our diffusing wall to be super thin, so we don't want to line it with mucus, right? Because we want the blood to be in close contact with the air, or we, the designer. So that mechanism doesn't exist. So then it's cleared through the lymphatic system or the blood system. So it has to be incorporated in the body before you can clear it out of your alveoli. So that's one of the reasons that the tiniest particles, the ultrafine particles, are so dangerous, is because they make it past those natural defenses that we had for the medium and large-sized particles. So what are the main factors influencing uptake? So the inhalation dose is a major one. So that's the amount that we breathe in is a big determinant of the amount that we keep. There also, the pollutant characteristics make a difference. So smaller particles, a higher portion of those will get deposited into your respiratory tract than larger particles will. And then for gases, more blood-soluble compounds, and that makes sense. The more affinity it has with the blood, the more it will get absorbed into your blood. There's also some respiratory and physiological effects. So deeper breathing and more oral breathing bypasses more of their defense systems, and you'll get higher deposited fractions of particulate matter. Cardiac output is important because with greater blood perfusion of your lungs, there's more opportunity for gas uptake. This is especially important for perfusion-limited compounds, like most of the VOC are. And the metabolic rate is important because what happens with the gases is that as you absorb them, your blood concentrations will approach a near steady-state equilibrium with the ambient concentrations. And then at that point, the rate of uptake is equal to the rate of metabolic clearance, or the rate at which you're clearing the compounds from your blood through your liver and kidney systems. So the faster you clear it, the more you're going to uptake. The more new pollutants you're going to uptake. So what are the impacts of exercise on uptake? Well, uptake doses across the board increase with exercise. But it turns out that the primary mechanism that they do that is through ventilation effects. So in other words, we've already seen the main mechanism that uptake increases with exercise, and it's the increased ventilation that drove our intake doses. So we already looked at that. So let's compare uptake doses to intake doses. So in other words, we're asking what is the fraction or the percent of the amount that we inhale that we're actually going to keep and stay in our bodies. Well, it turns out that particles and gases are kind of different in this regard. So what happens with particles is that the uptake doses increase even more than the intake doses. And that's primarily driven by deeper and more oral breathing when you're exercising. So a higher percentage, not only have your total inhalation amounts gone up, but you're also retaining a higher percentage of those during exercise. So this is really problematic. For gases, it's slightly different because, like I said, the amount that you absorb is going to be limited as you approach this equilibrium condition between your blood and the outside air. And so if you compare the uptake dose of gases to the intake dose of gases, it's actually slightly less. All right? So it's still higher during exercise, but not quite as much as intake doses or for particulates. So what do we have in the literature? Well, we have 6 studies that have looked at bicyclist uptake concentrations. 4 of them modeled uptakes and found, as you'd expect, that they increase with exercise. Only 2 studies have measured bicyclist uptake. And one came from Italy and one came from London. Some researchers in Italy looked at urban and rural bikers, and they measured metabolites of those BTEX compounds, which are VOCs, in the blood. And they found that the urban bikers had been exposed to more VOCs than the rural bikers. It makes sense. It's good that we have some empirical data supporting this, but it, again, doesn't tell us a whole lot about how to design our transportation system to mitigate uptake. The other research coming out of London, they sampled induced sputum, which is basically they sampled the mucus lining of your lungs. Induced sputum is they spray some saline to get you to expectorate some mucus. And then they just analyze it with spectroscopy looking at the black carbon content, so just the absorption of it, to look at basically the mucus in the lungs of a bicyclist and a transit rider in London. And they found, again, that bicyclists had higher black carbon deposition in their lungs than transit riders. And that makes sense because black carbon is one of the particulates, so that's going to be especially negatively impacted by or exacerbated by exercise. There's still pretty few direct measurements of uptake for bicyclists. Here again is where we're trying to fill some of the gaps in the literature. And we've taken a new approach because, again, we're really interested in more detailed transportation system characteristics and how they correlate with uptake. So we're using a new technique where we're breath sampling in bags. And this is something that comes out of the medical literature, in fact, because so they're developing breath sampling as a non-invasive, cheaper way of screening for diseases. Because it turns out if you have certain kinds of like liver and kidney diseases, certain VOCs will accumulate in your bloodstream, and then they can detect those in expired breath. And it's a good mechanism for screening for various diseases. And that literature, the medical literature, has shown that end-tidal breath, so the last part of your breath after you've gotten rid of your dead space air, is a really good proxy for blood concentrations. And this is particularly true for low water solubility VOC that don't interact too much with the lining in between your alveoli and the outside air. So they don't interact with the lining as they're coming out or the saliva in your mouth. And so we can use breath concentrations as a proxy for blood concentrations as a much easier way of sampling uptake at different points in the transportation system. One thing I will point out, though, is that this requires very precise instrumentation because we're measuring at environmental exposures really low, extremely low concentrations of these compounds. Luckily, we have that in the form of Jim Pankow's amazing, fantastical lab. And so those guys are awesome at doing these high-precision VOC gas analysis. So with the same instrumented bicycle routes, we've been taking intermittent breath samples. We have 75 breath samples from 9 days using 3 different subjects. And each one of those samples we analyzed for 123 different compounds, the concentration of 123 different compounds. Up here you see, this is one of those breath sampling bags, that clear bag, that's what it looks like. There again is the respiration monitoring strap. And this is just a simple incentive spirometer to help calibrate our respiration measurements. So here's what the sampling looks like. Again, Mount Tabor is our clean reference location. So we'll take a breath sample after spending some time there to equilibrate the blood concentrations at that low background reference level. Ride on facilities of a similar type, such as local streets or bikeways, on about a 20 to 30 minute segment. So we have enough time to get a good ambient sample during the ride. At the end of the ride, we'll take another breath sample. And then we can look at the exposure along the ride and changes in breath concentration before and after. And then we'll ride on, so this one is local roads. Then we'll ride on major arterials in another segment and compare the before and after breath concentrations with our ambient exposure concentrations. And we're also doing this with paired subjects, so we can see if the uptake is consistent for different people in the same conditions. So the early results, I think the really exciting thing is that the method works, is that it's a way to measure high-resolution uptake for people moving in the transportation system. This doesn't have to apply to bicyclists. It can, anyone moving throughout the city, this is a way of sampling their blood concentrations at intermittent points. Some of the modeling shows elasticity of breath to exposure concentrations of 0.3 to 0.5. What that means is that for a 10% increase in your exposure, you're looking at about a 3 to 5% increase in your blood concentration of the volatile organic compounds. And this is just for the traffic-related VOC, so not for all 120 of them, because some of them are endogenic, so some of them, like isoprene and acetone, you're generating in your body, and some of them are also just ubiquitous in the urban environment, so they wouldn't really be higher necessarily in traffic environments. We're finding some significant history effects where if your ambient or breath concentration before the ride was particularly high, it's still a little bit higher than you'd expect at the end of the ride. But the exposure concentrations are still important, more important than the history effects. And we're finding minimal subject-specific effects, meaning that these uptake fractions are pretty consistent, are not significantly different amongst the different riders. So it's pretty consistent across people. And here is a typical example. This is for benzene. We're looking at ambient and breath concentrations, percent increases versus our Tabor reference environment. And we've included 3 different facility types on here, a major arterial, local roads, and the I-205 path. So ambient concentrations about 2.5 times higher on the major arterial and about 75% higher on the local road than the Tabor. And then the same general pattern for breath concentration changes, but a little more muted, right? Because that's the 0.3 to 0.5 elasticity. So breath concentrations after biking on a major arterial about twice as high, and on the local road and the I-205 path about 30–40% higher than at our clean reference location. Okay, so that gets us almost all the way through that bike exposure pathway. But the last thing I want to talk about is health effects. So there have been 11 biomarker studies for bicyclists where they're looking at trying to measure direct indicators of health outcomes. And here we have pretty inconsistent results. So 4 of them found no significant acute effects at all. The other 7 found some significant acute effects. But in all those, most of the effects were insignificant, but they might have found 1 or 2 that were significant. Now, the problem with these is that the health implications aren't always clear. So these are indicators of, say, lung inflammation or systemic blood inflammation or cardiac stress, things like that. But they aren't exactly health outcomes. So it's hard to translate these indicators of some effect into things like morbidity and mortality, things that we can more easily quantify and consider in like a cost-benefit framework, for example. And these are all acute studies. So none of them, so we still don't really know the chronic effects of someone who's a daily bicycle commuter who's experiencing this kind of pollution uptake. So still a fair bit of uncertainty about the health outcomes of uptake while bicycling. And yet, that hasn't stopped a handful of intrepid researchers from trying to do the big net health assessment, right? So a number of studies have tried to say, what's the total effect of an increase in bicycling considering physical activity changes and crash changes and pollution changes. Well, I spent all day looking at pollution, and I know that that's really hard to estimate. And I'm sure those of you that work with crash data can say, well, that would be incredibly hard to estimate. And those of you who work in physical activity would be like, well, that would be incredibly hard to estimate. But still, you can use some pretty coarse methods, some rough tools to try and get at this. And those that have done it have found consistently that the physical activity benefits outweigh the crash or the pollution risks by an order of magnitude or two. So 9 to 96 times more physical activity benefits than the crash or the pollution risks. So my point is not that bicycling increases your intake doses, so we shouldn't do it. The point is that here's a pollution risk that here's a health risk of bicycling that we can, if through careful research, we could do a better job of quantifying and trying to find ways of mitigating for travelers. So that brings us to our conclusions. Both the literature and some of our early results have shown low traffic facilities to have much lower exposure concentrations than high traffic facilities. How much depends on the pollutant, but for the highly traffic related pollutants like these VOCs that we're studying, it can be double or even more, closer to triple the exposure concentration. Respiration is a major factor in terms of bike inhalation and uptake doses. And it really isn't sufficiently studied, especially if you're interested in how the transportation system impacts respiration with things like stop signs and road grades and things like that. And finally, the uptake rates and health effects really still not well quantified and something we all need to spend, we in the research community need to spend a lot more time working on so we can provide tools for decision makers to make more informed planning and design decisions. The future work, as I keep calling these things early results, so we now have a novel set of empirical data, uptake measurements, but there's lots more to do with it. First, we're going to continue the exposure and respiration models and try and get some more numbers there. Then the next step will be providing some bicycle network and facility design guidance so that, again, decision makers can more explicitly consider pollution dose impacts of the different options that they have. And finally, I'd really like to extend this to pedestrians, the other large group of transit or active travelers with higher respiration rates. I think it'd be interesting to do, and all I need is some of your money. So thank you all. Again, the literature review piece of this is coming out next month in Transport Reviews if you're interested, and I can get you a copy of that if you want. And then the early results piece was presented at the Transportation Research Board meeting in January, and that's available online, or you can contact me for that. I'd like to thank, for support of the research that we've been doing, especially the empirical work that we've been doing. The City of Portland, Metro, NHTSA, OTREC have all provided direct financial support to the project, and then the NSF supports me in my dilly-dallying. So thank you very much, and we can open it up to questions, I think.
Thank you. Really good research and I think very useful. I spent a lot of time developing Portland's neighborhood greenway system, and one thing I notice about the networks you're using is that some of them are kind of older facilities where we'd be comfortable, under 3,000 cars a day, and today we're building facilities that are more about 500 cars a day. So when you're on Lincoln and Clinton and those kind of things, you're on streets that actually have more traffic than, say, you're on Going or Concord or, those kind of things. And I wonder, what happens when you get finer grain in the low traffic settings of what the exposure impacts are when you're on a street with, like a Going, which has about 400 to 500 cars a day, versus a Clinton, which has about 3,000, 3,200 cars a day.
Yeah, that's a great question. So it's something I'm working on. So the first pass was just to use facility classifications from the Transportation System Plan. But I'm currently in the midst of GIS work. So we have some count data at the link level. It's interpolated some of its old counts, but absolutely in the next phase we'll be running models to try and get percentage changes in exposure as a function of ADT. So that is an intended outcome. I can't say yet that we're going to have significant results, but I hope to. And I think that's a good point. Thanks. I think back there was next.
You mentioned that around 205, I-205, the bike path along there, that they were unusually or unexpectedly lower in pollutants than you would expect right next to a freeway. How far away do you need to be from a lane of traffic to experience marked lessening of pollutants?
Yeah. So good question. So we're not going to have enough variation in that factor in this analysis to have answers for you, but it is something that's been looked at. And if you're looking at major roadways, the zone of influence, typically you're looking at 1 to 500 meters, and in terms of concentration still elevated above background levels. And when they do measure, if you do a concentration profile of a roadway, it kind of looks like this bell-shaped curve, right, where there's decay with distance. And it turns out that there's significant differences based on the lifespan of the pollutants. So some of the pollutants are rapidly transformed in the environment, like UFP don't last too long, whereas larger particles last a lot longer. Carbon monoxide has a longer staying power than some of the VOCs that are more reactive and get oxidized more quickly in the environment. So one answer is several hundred meters. The second answer is it depends on the pollutant that you're interested in. Does that work?
So like moving a bike lane 10 feet further away really wouldn't do that much.
It would still be in the zone, but you would expect it to be lower down the gradient. So we would expect the farther you get away, the lower the concentration to be. But it would still be elevated above, a background level. But there was some research here that they were just looking at about 8 feet, and they measured a difference. And some research in London, they measured the inside and the outside of the sidewalk, and they measured a difference. But both were elevated. I think you're next.
My name is Trey Gundel. I really love your research bike. The thing looks awesome. You were talking about possibly finding ways to generate similar data, but it's somewhat less cost, or maybe in a more modular type of system. Are you looking at doing some sort of Arduino and some cheap, sensors to, have something that's more deployable that you could generate, you could build 10 of them fairly cheaply?
Yeah, absolutely. So the ACE device, so like I said, there's an application and a device. The device is built on an open source Arduino platform. If you go to my website, I have all the source code there for the Arduino. I have all the source code for the Android application freely downloadable. I also have it on GitHub. Bigazzi is my username at GitHub, and you could download the source code to do all that stuff. And one of those ACE devices costs about $200, depending on if you put a GPS device in there or not, for the pieces to put it together. And I really want to, over the next year, we found pretty good correlations, correlation coefficients of roughly, let's say, 0.8 with the high accuracy devices, which I think is probably good enough, although that's one thing I haven't looked at is whether we can identify all the hotspots, for example, with the ACE data. But that's absolutely something I want to do is just try and find some funding to make a few dozen of these and give them to people for a couple weeks and basically crowdsource exposure data. And then returning to, the benefit people would get is that they would have direct data on their own exposures, and they can collect data wherever they are interested in having exposure data. Yeah. In back? This point.
Yeah, great job. It's really interesting research. Curious, I know you said when you were doing the data between taper or taking the different breath samples, I'm just curious, how long about do you need to take the sample after you ended a trip for that to be relevant? Do you always have this carbon exposure and all the different VOCs and stuff? Do you just keep it with you, or is it the amount that you're breathing? And just curious.
Yeah, good question. So as soon as you leave the high exposure environment, you're going to start to clear it. So instead of it being absorbed into your blood, it's going to be desorbed from your blood into your air, and you're going to be exhaling more than you're inhaling. So you want to take it immediately after the trip. One of the things we've looked at is including in this is the variability of the exposure on the link, and that turns out to be a significant negative variable. So if there's more variability, your end ride breath concentrations are slightly lower, and that's likely because you've off-gassed, essentially, a little bit of the VOC. So you want to take it immediately after. Yeah.
My name is Abhinav. So in general, I looked at very few people actually done research on it, like in every different areas. What do you think the reason behind that? Why is there such low numbers of research on this topic?
Yeah, so that's a good question. Part of it is technology-based. So we have a lot better tools now in terms of, for example, the TVOC instrument that we're using is less than 5 years old. The respiration monitor uses Bluetooth technology, which has really made these things cheaper, lithium-ion batteries. Things are getting cheaper and easier, more portable. So there's technology making it easier. But I think the other piece of it is that because a lot of the studies have, the main research question is this mode versus that mode, so they aren't as interested in the respiration characteristics and the physiology of it, which is really only comes into play if you're comparing active modes with inactive modes. So if your focus is on, auto in this, auto versus bus versus taxi, and one of them was looking at a CNG bus versus diesel bus, these kind of things, and then we'll throw in a bike and a ped too, then they're not going to want to invest a lot of time and money getting into the physiology and the respiration, which is why I think it often gets, well, we'll just do exposure concentrations and leave it there. Because it isn't really a core of the research question, is my guess.
42 seems like a very low number of research on
Oh, you mean measuring bicyclist exposure at all? Yeah, I think that goes back to, it's a lot of expensive equipment to put on a bike. And you have to find people who, it's easier to find volunteers in Portland than other cities to just bike around.
The other policy area that I think this might be interesting for is the Urban Forest Action Plan. When we are building neighborhood greenways, that's one of the things on our mind. How do we plant more trees for a lot of reasons, but one of them is air quality. And I wonder if you look at the same corridor, like say a Houghton as it parallels Lombard or Concord as it parallels Interstate, and the tree density through those corridors, what does that do in terms of the effect on air quality and the type of impact that adjacent busier street has through the corridor?
Yeah, that's a great question, and that had not occurred to me. If anyone has a nice, ready-to-go GIS layer with tree coverage on it, and you kind of send me a link to that, I'd appreciate it, because that'd be.
Start with the urban forester or with Friends of Trees, and I think
There might be a tree inventory out there.
Okay.
Arliss has got it.
Yeah, I was going to say,
Did I?
I'm sure Arliss has.
Okay, yeah, I hadn't thought of that, but that's an interesting idea, and try and get some indicator of that for the route and see if that shows up as a discriminating factor for exposure concentrations. Thank you.
Nicholas Coble. I was wondering, so looks like the major independent variable you looked at was the road classification, but I was also wondering if you tried getting some data on like traffic counts as you're biking down the roadways.
Yeah, so we started with functional classification because, like I said, these are the early parts. And as I mentioned before, a next step is looking at it with ADT, or average daily traffic. So those are the acronyms. So we're going to be, so that'll be one of them. And then the second, but that's static, right? And some of the counts are pretty darn old. So the other piece of that is we do have live, like 15-minute and higher resolution traffic data from a few points on there. So I'm going to be looking at different ways of kind of taking the ADT and adjusting it based on the traffic concentration at a few representative points on the network. But that'll definitely trying to get to the idea of this percent per extra vehicle. I think that'd be interesting. Yeah.
Some of your findings seemed like they were kind of intuitive, but I think your research was still important because it, quantified things. But did you have any findings that you found to be particularly surprising to you?
So the One of the things we're still looking at is the Springwater Trail had some pretty high concentration spots along it. And we're looking at possible relationships with nearby land uses. And I didn't want to focus on that because it's still, we're still looking at, pulling out the video data and looking at what exactly was going on when we were there. So that was one of the surprises. And like I said before, I-205 was a little lower than I would have expected. I thought it was going to be closer to a minor arterial, but seeing that it was closer to a local road, just from what I would guess was surprised me a little bit.
We've run out of time, so thank Alex again for
Thank you all.